Have you ever stood at a harbour, gazing up at a colossal cargo ship? It's a remarkable sight, these behemoths of the sea, laden with tons of goods, yet seemingly gliding effortlessly atop the water. How do these massive structures, weighing thousands of tons, manage to stay afloat? The answer lies in a fascinating interplay of scientific principles, primarily buoyancy, and Archimedes' principle. These principles explain why a small pebble sinks while a gigantic ship floats. It's not magic, but rather a testament to human ingenuity and our understanding of the natural world. Join me as we delve into the captivating science behind these floating giants. This journey into the heart of buoyancy will unravel the secrets behind one of humanity's oldest and most vital technologies. From the humble canoe to the modern cargo ship, our ability to traverse the seas has shaped civilizations and connected the world. Buoyancy is the upward force exerted by a fluid that opposes the weight of an immersed object. Imagine diving into a swimming pool. You feel lighter, almost weightless. That's buoyancy at work. The water pushes you upward, counteracting gravity's pull. The same principle applies to ships. When a ship enters water, it displaces, or pushes aside, a certain volume of water. This displaced water exerts an upward force on the ship, the buoyant force. If the buoyant force is equal to or greater than the ship's weight, the ship floats. It's as simple as that. Think of a beach ball. It's filled with air, making it lighter than the water it displaces. The buoyant force acting on the beach ball is much greater than its weight, so it bobs effortlessly on the surface. The relationship between buoyancy and a floating object's weight is beautifully explained by Archimedes' principle. This principle states that the buoyant force acting on an object submerged in a fluid is equal to the weight of the fluid displaced by the object. In other words, if a ship can displace an amount of water equal to its own weight, it will float. This principle is the cornerstone of ship design and explains why ships have such vast hulls. The enormous size of a ship's hull allows it to displace a massive volume of water, generating enough buoyant force to counteract its weight. Archimedes' discovery, said to have come to him while bathing, revolutionized our understanding of buoyancy and laid the foundation for the design of ships and other buoyant structures. Another crucial factor in understanding why ships float is density. Density is a measure of how much mass is packed into a given volume. Objects denser than water, like a rock, sink. Objects less dense than water, like a piece of wood, float. Ships, though made of dense materials like steel, are designed to be less dense overall than water. How? The secret lies in their shape and the inclusion of large, air-filled compartments within their hulls. These air-filled spaces significantly reduce the ship's overall density, making it light enough to float. It's like comparing a solid ball of clay to a hollow clay pot. Both are made of the same material, but the hollow pot, with its air-filled space, is less dense and will float. Section 5. Shape matters. The role of displacement. The shape of a ship's hull plays a crucial role in determining how much water it displaces. A wide, bowl-shaped hull displaces more water than a narrow, V-shaped hull. The more water a ship displaces, the greater the buoyant force acting on it, and the more weight it can support. Shipbuilders carefully design the shape of the hull to maximize displacement and ensure the ship can carry its intended cargo safely. The shape also affects the ship's stability and resistance to waves and currents. Think of two identical pieces of aluminum foil. One is crumpled into a tight ball, while the other is shaped into a wide, shallow bowl. The bowl shape will displace more water and float, while the crumpled ball will sink. Section 6. The balancing act. Stability and center of gravity. While buoyancy keeps a ship afloat, stability ensures it stays upright and resists capsizing. Stability depends on the ship's center of gravity, the point where its weight is concentrated, and its center of buoyancy, the center of the volume of water it displaces. A stable ship has a low center of gravity and a center of buoyancy that shifts in response to the ship's movement, creating a righting moment that helps it stay upright. Ship designers carefully distribute weight within the ship to achieve optimal stability. Imagine a pencil standing upright. If you push it slightly at the top, it tips over easily. However, if you add a heavy weight to the bottom, lowering its center of gravity, it becomes much more stable and resistant to tipping. Section 7. Marvels of engineering. From canoes to cargo ships. The principles of buoyancy and Archimedes' principle are applied in the design of all kinds of floating vessels, from small canoes to massive cargo ships. Over centuries, shipbuilders have refined their techniques, developing innovative hull designs and utilizing advanced materials to create ever larger and more efficient ships. Modern cargo ships, for example, are engineering marvels. Their massive hulls are divided into numerous watertight compartments, enhancing buoyancy and safety. Ballast tanks, filled with water, are strategically positioned to adjust the ship's trim and stability. The story of ship design is a testament to human ingenuity and our ongoing quest to push the boundaries of what's possible. Section 8. Beyond buoyancy. Other factors at play. While buoyancy is the primary force keeping a ship afloat, other factors also come into play. Hydrodynamics, the study of how objects move through water, is crucial in ship design. Factors like water resistance, wave patterns, and wind forces can all affect a ship's stability and performance. Shipbuilders use sophisticated computer simulations and testing tanks to optimize hull designs, minimizing drag and maximizing efficiency. They also consider factors like propulsion systems, steering mechanisms, and onboard systems to ensure the ship operates safely and efficiently. It's a complex interplay of science, engineering, and design that allows these massive vessels to navigate the world's oceans. Section 9. Conclusion. A delicate dance of science and design. The next time you see a giant ship gliding across the water, take a moment to appreciate the intricate dance of science and design at play. It's the power of buoyancy, explained by Archimedes' principle, that keeps these behemoths afloat. It's the careful consideration of density, shape, stability, and hydrodynamics that allows engineers to design ships capable of transporting vast quantities of goods across the globe. The story of ships is a testament to human ingenuity and our enduring fascination with the sea. It's a story that continues to unfold as we strive to build even more efficient, sustainable, and awe-inspiring vessels to navigate our planet's waterways.